Thanks a lot. So my name is Ravi. I'm from VMware. Um, this topic is really going to make you guys go to sleep. So get ready. Uh, at VMware, I'm part of a team that works with Kubernetes a lot, onboarding companies, enterprises into Kubernetes. And what we have seen lately is the intersection between dev and ops, developers and operators, is getting meshed, right? And that's where I work with, right? So my background is I've been a developer for many years, and for the past few years, I've worked at onboarding cloud at different companies, and being part of Pivotal and VMware, and working on the Kubernetes side of things. So this talk is a motivation to kind of cross the bridge and understand what kind of challenges happen in that gray area intersection, which you call Devops, and today it's becoming SRE, and definitely touch upon platform, cloud native platform, what kind of services, and how Redis and Rust is being applied to kind of solve those challenges. So DevOps is definitely an operator and a developer story today. Many teams have been spun up where they are operationalizing Kubernetes platforms, right? And the challenges that they face are they have to do a lot more with lot less. They're not being given anything more. And so gone are the days where you'll find a lot more hard iron to throw at and solve that challenge, or have a beefier memory or a CPU and storage. In the cloud, everything is metered. In the on-prem cloud, everything again is metered. So you have to do pretty much a lot more with a lot less. And that's where the story evolves. So in my going around with these companies, I see that DevOps teams are being constantly challenged to mesh with the developers. Services that are being applied on the operator side have to be used by the developer side. Services cannot stop. This is a cloud native platform. So essentially, there's a contract with the users that nothing can go down ever. And so operators and developers are coming to a place where they realize this is almost a 24/7 operation, right? And so you need kind of services and cloud native kind of applications that go with it to be up and running all the time. There isn't a time that they can go down. User base is increasing, and failure is to be expected only because there's a lot more complexity in this space. And so platforms are becoming distributed. That's another kind of pattern. You see a lot more places where different services are on-prem, some services are off-prem on the cloud, and they have to interact. An application, the concept of an application today is that can be deployed almost seamlessly anywhere. It might have pieces of it on-prem, talking to things, let's say on Google Cloud or AWS or Azure. And this constitutes an application. So if something goes down, the whole team gets affected. Everybody is under stress. It's difficult to pinpoint problems. And especially on the Kubernetes side of things, it appends the model. So historically, operators know how to write scripts. They do automation. They can go clean up things. They can apply some artifacts that have already been written for their environment. But with Kubernetes, what do you do? It's a new model, right? It works on SREs, which is the verb that Kubernetes understands. It has a concept called as controllers. There's an event loop inside Kubernetes that you have to tap for everything. So if you deploy an application on Kubernetes that talks to an application that's sitting on-prem, outside, you have to kind of manage and orchestrate these things together. That's complex. And then you have these services which are coming and going. So debugging, logging, looking at this from the standpoint of understanding where the problem fault lines lie, is often difficult. So what we are seeing today is a lot of, at least in my limited, experimentation, you need services that are always up and running 24/7. You need services that follow the cloud-native patterns of concurrency, reliability, and almost now uptime that is unparalleled before. So there are no downtimes to contend for. Companies are looking at keeping things up and running, almost on a scaled-out pattern. So with this in mind, I was toying with the idea of putting, let's say, an app, right, that played with Redis. I like Redis a lot. I come from the Cloud Foundry space where we have Redis as one of the key services onboarded. And so I've seen Redis kind of attempt to go easy to deploy, easy to use, easy to scale out, all those easies. So I was looking at an application that we could understand how to deploy and come up with a pattern to kind of see if that solves the challenges in the DevOps space. So Rust and Redis. So there's a lot of libraries on Rust. Rust is a very new language. It is concurrent. It has safety features. It has security. It is built around the concept of having futures and closures. That means you can almost assume it to be threat safe. It has other things. We'll go through. We'll go through those items. So one of the key things that Rust, motivation for Rust came up was how Bugzilla, almost 7 or 8 years ago, started looking at replacing some of their code bases on CSS selectors in the Mozilla Firefox browser from C++ to another language, and that's where they formulated Rust. And so the motivation of Rust was to be highly performant. And there's a screenshot here that shows how it took them many years for a bug that was opened in 2011. You're able to see that on the red, which basically promised feature request on the Mozilla browser. Somebody said, hey, we need to parallelize our CSS operations. What that means is they need to do things in parallel, not in serial. And that's not non-blocking as such. So everywhere you go, you find concurrent systems being written, and that's the bedrock of platform in the cloud-native space today. They have to be performant to expectations, right? And so that thing about you must be this tall to write concurrent code is, in reality, a difficult thing to achieve with other code bases like C++ or C, or even Java and other languages. And that's what Rust aims to solve behind the scenes. So what are the building blocks for Rust as such? So it's built on zero cost abstraction. All that it means is it does not have a runtime. So unlike Java and others, which you have to have a garbage collection, Rust does not have that. It does the checking at runtime at the statically linked compile time instead, right? So it brings all those checks and balances at compile time and forces the developers to adopt a series of patterns that you can be good at writing code now than to pay for it later. That's the mindset. Then you have things like futures, which are in every other language, but Rust has it too. And Rust borrows some of these ideas from C++ and C. You have ownership and borrowing, which we'll talk about. So we'll talk about futures, concurrency, ownership, and borrowing to understand how it does memory safety and data race freedom. So remember, the choice of a language determines how we can solve certain challenges. And in this case, Rust is able to perform to a throughput of, multi-millisecond kind of response. The kind of response that Redis kind of talks about, right? So you've heard Iftak talk about these things at his presentation where he's allowing or is going after the goal that Redis is performant and its response times are very short. And that is what Rust's building block and goals are too. So coming to Rust, it has these features built in. Coming from studying other languages for the longest time, the Rust implementers settled on things like ownership and borrowing is one. So here is a use case where you have two functions. A function main is letting a mutation of a particular vector. And the function on the right, which is function take, is taking those things that are pushed on the vector and modifying it. So in this case, if this was a code written on C++, at some point, there will be a dangling pointer that will allow things like segfault to happen. Here in Rust, there's this concept of ownership, which transfers the ownership of those variables to the calling function, which in this case is take. So the main function has no knowledge now or does not own these variables. So if you suddenly go and try to modify the variables again after calling the function take, you might cause a segfault. In case of Rust, it'll throw a compile time error. So things like this, which introduce bugs, are kind of hard to do on the Rust platform. So ownership and borrowing are the key fundamentals around which Rust allows us to do thread safety, no data races, and safe memory utilization. It kind of does the auto-incrementation of function pointers, so you're able to kind of understand what is incremented and what's decremented. It takes care of those things internally for you. The other concept is concurrency, which is where a lot of performant code we're trying to understand today. In the cloud-native space, everything, almost every other service or application is in multiples of many, right? There isn't an application that is run as one instance. There's multiple instances of an application, especially in Kubernetes, behind a clustered API, or cluster whip, or an ingress controller, or a node port. These are the abstractions to allow things to fall down, so you're still able to reach to a service in the back. So similarly, in Rust, the concurrency pattern allows you to kind of keep going and maximize on the performance that you get out of running an application in a single-threaded model. So that way, you're not able to so concurrency, so let me backtrack. So concurrency is not parallelism. This is a quote by Rob Pike, the creator of Go. It's a very great story where he relates to how you can parallelize, but concurrent application, the thought is in design. It's not in writing code. So you can make these services decomposable, which attack the same space and can do multiples of the same thing. So that's the concurrent model that we're looking at. So what do you call it? Rust does it in a way that it's seamless behind the scenes, using its own internal logic. So you don't have to think about and fathom about how to write a concurrent code. And that's why it's kind of the building block for some of the other services that we'll talk about. So this is all going towards us writing performance services, concurrent code, using less CPU and memory, almost making use of the same core or multiple cores. So the idea here is we're trying to go towards an application space that is becoming more and more workable, is more resilient to failures, and is able to kind of be more up and running. That's what we would like to see in a space which is the intersection between platform and code and application. At least that's the idea. Any questions I can take? The third piece is async futures, and that is what are designed today. I'll show the code. So async is another topic, hot topic at least, from the standpoint of services. You open new ports, you open TCP sockets, you open Unix UDP sockets. These are things that happen on the I/O side of an application. Again, the same thing, non-blocking versus blocking. So the notion of blocking versus non-blocking is in C++ or C, if you write a code, you're able to kind of block, have a blocking process. So in this example, I think, in this example, you can say the int main is calling a PID fork, right? It's forking off a next process. So there's a main process, and there's a separate fork process. These are two processes. And this printf might print a 0 and a PID number, which is the fork, or a PID number and a fork main, which is 0. So you can kind of understand having a little concurrency, even a small code base like this, is meaning that you'll have to manage the thread processes as well as the state of the application. So in this case, the PID number, right? So when concurrency, when you see stuff like, yeah, it's not moving. There you go. When you do I/O, async I/O, that is where the building block of an I/O operation happens. So you run a web server, you run a service, you run something in the backend that's a daemon. These are using I/O blocking, non-blocking I/Os in async within Rust using concurrent patterns. So to give you a summary of this, the three blocks that we saw is concurrency, I/O operations, and async methods, and borrowing and non-borrowing kind of concepts within Rust that allow you to be fearless about writing concurrent code. In our case, Tokyo is a library that we are going to showcase in our code, which is built on these abstractions. Everything in Rust is built in modular fashion. Concurrency is not main part of the language. You'll have to borrow those crates or dependencies to write a concurrent code. The philosophy is that you know best to choose the concurrent mechanism that you're going after. So Tokyo is one of those things that you can choose to write services on top of. So this is where you start really writing web servers. The ones that I showed you are building blocks to create a web server. So in this case of Tokyo, it is event loop, much like Redis is. I was sitting here and watching someone present on the internals of Redis that shows the event loop. In our case, these are green threads. It is not the OS thread, but Rust managed threads. Again, it has ownership and type system that allows it to do something like back pressure, and there is no garbage collection, meaning this can be installed on devices and places that are very memory and CPU intense. So we saw Rust. Taking a look at Redis, some things that I personally like and I've seen developers use is you have pub/sub, you have streams. Streams is a very important concept and abstraction today, where it lets you manage heavy amount of volume of data that's coming in, and developers are able to pinpoint and do event-based architecture. So there's an event that came through, and you're able to tap into the stream and understand that particular event, and kind of borrow on that and do other things or kick off downstream services. Then you have a thing called global CRDT. Remind me again, CRDT stands for? Conflict-free. Yes. So it's a type, right? It's a T for type, right? data type. Right. So all that is it's another way of doing CAP, which is CAP, consistency, availability, and partition tolerance. And that allows you to be highly consistent in terms of access to database and performance. So these are things that have been thought about inside of Redis. Now, as a developer, I'm not pushing limits like you guys would be, right? I'm writing code in the gray zone between operations and deployment and cloud and development. So these are tool chains that I'm using to go and solve those problems. I'm using Rust, I'm using Redis, I'm using Go. If you in the place where you want to understand the internals of Kubernetes API, you necessarily have to tap into Go or Rust. These languages and services, having provided in the concurrency platforms, async IO, futures, where the future is basically where a construction of abstraction that allows you to understand that there will be a future date in which you can get the data. And so that allows you to do non-blocking kind of async operation. So these paradigms allows a lot of flexibility for developers like me who kind of understand that the community is kind of doing the best understanding of which patterns to fold in to the services. So Rust and Redis, I think there was a slide that says that it's peanut butter and jelly for me, only because they have the right set of abstractions. I don't have to worry about what will happen if they fail. There are ways in which I can mitigate that, but I'm in good hands if I'm able to kind of use those to solve my problems. So obviously, users in the wild just gives us a high level of who's using Rust today. It came from Mozilla, so I think the Firefox browser today says a lot of the code has been shifted to Rust. Definitely take a look at that. Any questions I can answer? I'm going to go into a demo at this point. So let me oops. Oh, man. Yeah, let me describe it. I know it's hard to see the code and somehow it's not behaving. So I've got a Rust server that's, I've got a Kubernetes deployed on AWS. It's a pod running with a 3-node cluster. And it's kind of listening to me do kubectl deploy app, right? But I'm now taking Rust to plug into the API, Kubernetes API, master API, and deploying a pod that I've written, codified here. This is Rust that is taking the Kubernetes CLI and trying to understand the APIs and go through those pod APIs and deploy a deployment of a pod. So once I deploy the pod, what I've done is it will generate a pub/sub message into a Redis store that's running locally. And the Redis store then communicates, or there's an outside service, which is written in Golang that kind of plugs into the Redis store and subscribes to these messages. And so it's able to kind of externalize the event that's going inside Kubernetes. So as soon as Kubernetes deployment happens, it emits a pod received or pod created event. And so this is able to, Rust is able to capture that event, notify Redis about it, and Redis is now being watched by Golang. So this is kind of a pattern where we see, which is common, externalizing an event that is happening inside of Kubernetes that could be taken out only because these are applications, the pods are applications that are sitting and watching and talking to external services. So you're kind of able to orchestrate the deployment of a pod, deployment of an application on Kubernetes, and do other things based on those events external to those environments. So it could be adding more, I don't know, capacity in certain places, or creating or standing up new services, or maybe adding a more performant node to Redis. At 3-node cluster, I feel like, oh, a number of pods are increasing in this particular cluster, so let's increase the capacity for Redis. That could be one operation that you do. So this is a pattern. So I'll just run it, hopefully. Yeah, my thing is not working at all. So this is Rust. This is going to go and deploy a pod. This is Golang code that's watching at the events, right? I've already gone ahead and compiled the Rust application. And so it's gone ahead and deployed. And there you go. So it came back. So it deployed a pod that was named blog, has a particular number. It could be a random generated number. And this came into Redis. And Redis kind of transmitted that data over to, or the Golang kind of picked it up from the Redis kind of channel. So that's like talking about how you can integrate, or there are libraries in Rust that allow you to talk to Redis, and there are libraries in Golang that are allowing you to kind of integrate into Redis. Just a very simple high-level example, nothing very fancy about it. So going back to our presentation, pretty much that is the end of it. Any questions I can take?